Okay, welcome to chapter 23. We're going to start with a combined discussion of the Aldol condensation covering sections 23.1 through 23.3. First, the general reaction. In the general reaction, we have an aldehyde, and this can be also a ketone. And in fact, two of these react in the presence of a catalytic amount of a base. Now the base here can be hydroxide, or it's often an alkoxide, methoxide, or ethoxide. This is actually a reversible reaction, and the product is, and I'm going to draw this in a particular orientation so that you can see, there's the aldehyde that I started with. Here in yellow is the new bond that we formed. Again, the two carbons of the aldehyde, and we make an aldehyde, and it has a beta hydroxy, so an aldol. This is the aldol product. So this reaction is reversible. This is 21.1, sorry, 23.1. One on the brain there today. So for instance, if we use, let me look at this specifically, phenylacetaldehyde, and we treat that with sodium ethoxide, the reaction is reversible. The aldol product so again, I will emphasize the new bond that I made. We're going to look at the mechanism of this in a minute. And this has an equilibrium constant of roughly 10 to 90, or 90 to 1. Nine to 1, 90 10. So that reaction is favored to give you the product, but not all of them are, in particular with cyclohexanol. By the way, of course, there are two of these. So notice we're making a bond between the alpha carbon of one position, here's the alpha carbon, and the carbonyl carbon, or the one position of the other aldehyde. Now, if we do this reaction with cyclohexanone, the aldol product, so there's my aldol product. It is in fact disfavored. It's 78 to 22. So how do we make this reaction go forward? Well, it turns out it can be done in a pretty straightforward manner, although the first step is reversible, that is the aldol condensation. It then undergoes elimination simply by heating a little bit, and so this is 23.3, where you can read about that. And so this product would produce and let me use a squiggly line here to indicate there's a mixture of stereoisomers in that aldol product. So likewise, we can heat these reactions further. Just heat them up a little bit. And they will go to good yields. I don't remember what, I think, I don't remember that one, but I think the cyclohexanone, if I remember correctly, to produce, this is around 92%. So that's the aldol condensation in a nutshell. Now, how does this reaction occur? We need to look now at the mechanism. Okay, so how is the mechanism of this reaction going to occur? Well, we start with our aldehyde, and we've already learned about the acidity of the alpha position. And so with the base, particularly catalytic in base, remember with catalysts, we often start with the catalyst. So we deprotonate again, this is an equilibrium to produce the enolate ion plus ethanol, and that is reversible. Then here comes our second molecule. We know that enolates will react as nucleophiles. Turns out we have a self-condensation where the carbonyl, another molecule of the carbonyl starting material, so this would be our acetaldehyde, is the electrophile. So again, here's our nucleophile, here's our electrophile, and of course in the first reaction we had a base, and this was acting as an acid. So remember our mechanistic principles here: acid, base, electrophile, nucleophile. Bring the lone pair down. This swings out to form the new carbon-carbon bond. That alcohol or carbonyl oxygen will swing up. This gives us, I'll put the methyl group right there. An aldolate. Let me again emphasize for you the new bond. Here's the new bond that we made. Now, this is actually reversible. Even though it's a carbon-carbon bond forming, it's reversible. So to reverse that, I just need to push the electrons back to go back to the two molecules and break the carbon-carbon bond. So that's the initial aldol, and of course this can now, let me get the color here, this can react with a proton source and we would get the aldol product. So here is the aldol. Tell you what, I'll switch the color there. There's that proton. Now, all of this is reversible. When we get to this point, how do we get beyond that to the elimination product and what goes on? Well, this elimination is a new kind of mechanism. It's the E1CB. That's the unimolecular elimination from the conjugate base. So first we need to form the conjugate base of this aldol product. Well, one conjugate base we already have up here, the aldolate. Okay? But aldehydes are pretty acidic at the alpha position as well. We've seen some of those numbers. We've already seen the ethoxide deprotonate that, and so we have this process again. So we form the conjugate base from alpha deprotonation. Again, that step is reversible. And then here comes what is, in this case, an irreversible step. So we have our enolate, and it has alpha beta. It has a beta leaving group, the hydroxide. Remember, we're under strongly basic conditions. The way that we get this to go forward is with a little heat. So we're heating this up in this second step of the reaction, and this provides the driving force. And we eliminate the hydroxide. So in a unimolecular elimination process, so first in an equilibrium we make the conjugate base. That's the conjugate base. And then we do the elimination. To produce the alpha-beta unsaturated compound. And this is the irreversible step that drives the reaction to completion. For instance, we saw that for cyclohexanone. It favors actually not undergoing the aldol, but when we heat it up, the equilibrium shifts, and we can shift all of that simple Le Chatelier's principle again, all to the desired product.